Hello everyone, I am 𝗖𝗃𝗃𝗲 from Politecnico di Milano, and together with my colleagues 𝗂𝗲𝗃𝗂𝗲𝗃𝗃𝗲𝗍 and 𝗀𝗂𝗃 𝗂𝗃, I will present and discuss some optimization techniques and tools for the design time and runtime management of artificial intelligence applications. Once an AI application has been developed and is ready for deployment, the most appropriate resources need to be selected to run it. This process is complex and it requires multiple stages. Indeed, to determine the optimal placement of each application component, we need to know or be able to predict its behavior in terms of performance on the candidate resources where they can be executed. Once we have these, we can use them as a starting point to determine the optimal resource selection and component placement to support the application execution. As mentioned, the first thing we are interested in is predicting the response times of all application components on the candidate resources configuration. This will be crucial to support the selection of the optimal placement, minimizing costs and guaranteeing performance constraints. There are several strategies to achieve this goal. The first one is based on developing analytical models for the component's performance, for instance, exploiting the queuing theory. This has some great advantages, among which the fact that it requires only a limited profiling, that no time is needed to train the models, and that the response time computation is very fast. However, defining an analytical model requires some assumptions, for instance on the service time distributions, which are not always satisfied in a practical setting. The alternative is therefore relying on machine learning to train models that manage to predict the response times with a reasonable level of accuracy. Of course, in this case, we do not have to consider explicit modeling assumptions, and moreover, we get models that are specific for a particular component resource pair. On the other hand, however, building accurate machine learning models requires a large training set, and so a large profiling campaign in general, and also periodic retraining to avoid model drift issues if the conditions change. Let's now imagine that we have the performance models we need, meaning that we can actually predict the component's response times. We can consider the following example. We have a sample application that consists of a sequence of 7 components that identify and classify damages in wind turbine blades. The application processes images taken by a human operator using drones, and part of the processing can be offloaded to local edge devices, as for instance the operator's PC or cloud resources. The 7 components have various characteristics in terms of computational requirements and response time constraints, and can be executed on different candidate resources in the computing continuum. For instance, the first 2 components check the image quality and determine whether there are any damages in the blade part. Being lightweight components, they can be executed directly on drones, or for the second component on local edge devices. The intermediate components, which perform blade part identification and object detection tasks, can be executed at the edge or in the cloud, while the last components that perform the final damage classification are only compatible with powerful enough cloud resources. What we need to effectively run our application is to solve what is called resource selection and component placement problem. This encompasses a set of subproblems. First of all, we have to determine which resources we want to use at each computational layer. For instance, if we want a drone with or without GPUs, or if our operator should bring its laptop on site or consider a local edge server, or determine the type of virtual machines and the number of instances we want to rent from the public cloud. Then, we have to decide which neural network deployment to consider for each component, reminding that these components can usually be partitioned at different execution layers to offload part of the processing to different devices. And finally, we need to determine where to execute each component partition. These decisions will depend on the predicted response times, since we want on one hand to minimize the execution costs, and on the other hand to avoid violating response time constraints imposed by the users. First of all, we solve this problem at design time, before the application starts. Here, we usually consider a maximum expected workload to size the resources in a way that prevents constraints violations. However, the design time solution is not enough. The input workload usually varies at runtime, while the application is running, and we need to reconfigure the system to avoid saturating or underutilizing the resources. As you can see from the figure, the decisions we can take at runtime are limited, especially for what concerns edge resources. If we decided, for instance, to buy a drone with GPUs and to use an edge server on site, we cannot change our mind while the application is running because we do not have the other drone without the GPU, and other types of edge resources may not be accessible. On the other hand, we can always scale cloud resources considering a different number of VM instances, or we can decide to offload part of the processing to Lambda function if they are available, since the time to provision is usually almost negligible. Moreover, migration actions are always accessible provided that the components are compatible with the existing alternatives. In the following, we will present 3 components of the AI Sprint toolchain, designed to ease profiling and performance model development, to optimize the application execution and design time, and finally to adapt the system configuration at runtime to cope with varying environment conditions. Good afternoon. In the next 2 videos, we will present you 𝗖𝗂𝗲, a tool to support the automatic profiling of artificial intelligence applications and the generation of machine learning-based models for performance prediction. We are at this stage of the design workflow, where the application has been developed and is ready for deployment. As already mentioned, developing models that allow to predict the component's performance on different resources will be crucial to define their optimal placement and support the application execution. The problem we aim to solve with the 𝗖𝗂𝗲 tool includes 3 different aspects. First of all, we want to automate the application profiling, executing its component on several candidate resources according to the parameters set by the application developer in a suitable configuration file. Moreover, we exploit the integration with the infrastructure manager, or IAM, to guarantee that the required infrastructure is automatically deployed and configured. Finally, we want to use the data collected during the profiling stage to automatically train machine learning-based models for performance prediction. Why do we do this? First of all, if we have to test the application components on several candidate resources, we need to deploy and configure multiple infrastructures, which is usually a complex task. And second, because collecting all the profiling data we need to effectively train good quality performance models would require to manually test multiple different configurations, considering different combinations of components and candidate resources. As mentioned, the literature offers several techniques to support the application's profiling and the generation of performance models. The examples reported in this slide concern benchmarking tools that consider cloud-only, edge-only, and cloud-edge deployments. In particular, the first one focuses on applications executed on resources coming from public cloud providers as, for instance, AWS, Azure, and Google Cloud. The second one refers to edge frameworks and compares Greengrass with Azure IoT Edge. Finally, the third one collects latency-related metrics to support the application distribution across edge and cloud. When discussing the generation of performance models, the state-of-the-art explored machine learning as a tool to predict the sources of performance loss for microservices-based applications. Moreover, the response time on functional service systems is predicted starting from the average response time of warm and cold requests, the arrival rate, and the system expiration threshold. Differently from all the presented proposals, our tool is focused on benchmarking the 𝗖𝗂𝗲 framework, which can be deployed on top of any commercial cloud. Exploiting different regression models, it is able to predict the average execution time of AI application workflows with a mean absolute percentage error lower than 25%, which is considered acceptable for practical use, even after a limited profiling campaign. This is the general architecture of 𝗖𝗂𝗲 and the related components. It requires several input files providing the description of the candidate resources, which can include both physical devices and virtual machines, the application components with the relevant parameters and input data, and the hyperparameters required to develop the machine learning-based performance models. Moreover, the user has to provide some specific parameters that describe the profiling campaign, including, for instance, the level of parallelism to be tested, specifying whether synchronous or asynchronous calls should be considered, and whether we want to test the single components along with the full application workflow. This is something that is usually done to limit the number of experiments. If an application includes, for instance, two components with two candidate resources each, testing the full workflow on all the possible alternatives means combining the different candidate configurations in a combinatorial way, which is of course very time-consuming. Instead, 𝗖𝗂𝗲 aims at profiling the single components separately and use the performance models to predict the response time on the whole application. Once the input data are collected and processed, the cluster has to be configured according to what is required by the experiments. This is performed automatically by relying on the infrastructure manager and TOSCAR, both if the application components will run on a virtual and a physical cluster. When the cluster is ready, the profiling campaign can start. As I mentioned, we collect some profiling data on both the full application workflow and the silicon components, following this strategy. Imagine an application characterized by a single component, which however can be partitioned at a specific layer. If we consider two candidate resources, for instance a cluster of Raspberry Pi and a cluster of virtual machines, and we assume that the first partition can run only on the first candidate resource, the second partition can run only on the second candidate resource, and the full component can run on both, we identify the following three scenarios. Moreover, if we look closely to the third deployment, for instance, and we assume that the user asks to test the different level of parallelism for the two partitions, we see that our profiling campaign will include for the third deployment only 3 different runs. This explains why an auto-profiling tool is helpful, since running all these tests manually and possibly reconfiguring the cluster every time would be very complex and time-consuming. The profiling data collected during the previous stage are used to build training sets to develop performance models using AML library, a library for the automatic generation of regression models exploiting several techniques, ranging from ridge regression to random forest and XGBoost, for instance. The library allows to automatically perform feature augmentation and sequential forward feature selection, select the best set of hyperparameters for each method, and compare them using holdout, interpolation, and extrapolation techniques, to finally select the best model evaluated considering the mean absolute percentage error. Selecting the best model for interpolation and extrapolation overall means having something that, once it's trained with the execution times collected with, for instance, 1, 4, and 8 parallel instances, allows us to predict what happens when we use 2 or 6 instances, or instead 16 or 32. This is of course useful, for instance, when we want to know if it is worth it to add new resources to our cluster, which introduces some costs. In the following few slides, I will present some results we obtained with 𝗖𝗂𝗲 profiling and generating prediction models for a two-components application known as mask detection. Its first component processes an input video, splits this video into frames, and blurs the faces to guarantee privacy preservation. The second component processes the single frames and identifies and counts people wearing a face mask. We consider 2 candidate resources for each component and test the performance models on interpolation, extrapolation, and the ability to predict the response time of the whole application given the data collected on the single components. The data collected during the tests were used to generate and evaluate different machine learning models exploiting XGBoost, ridge regression, decision tree, and random forest. The main feature we considered is a parallelism level, which denotes the maximum number of available cores for all the services. Since all the components are single core, this is directly related to the maximum number of components that are running concurrently. These are the results we achieved when testing the interpolation capabilities of our models for the single services. As you can see, the mean absolute percentage error is quite small, reaching at most 10%. We built an additional model to predict the execution time on the full workflow. On the left, we see the results achieved when training this model on data collected for the full workflow. On the right, instead, we see what happens when combining the models trained for the single services to predict the whole application execution time. We note that even if the accuracy is lower, the mean absolute percentage error is still below 20%, thus acceptable in practical scenarios. Finally, here we report the results on extrapolation. In the plot on the left, we see the data collected when considering a variable number of input videos. We combine the 2 best models for the individual services and perform the extrapolation on the data from the last test, including 20 input videos, whose results we reported on the right together with the corresponding predictions. The mean absolute percentage error of the combined models is 9.75%, proving the good extrapolation capabilities of 𝗖𝗂𝗲. I will now leave the floor to my colleague 𝗖𝗂𝗲𝗄𝗲 who will demonstrate the use of the 𝗖𝗂𝗲 tool.
In the demo, I'm going to show the structure of the 𝗖𝗂𝗲 directory, an overview of the input file, and the execution of the 𝗖𝗂𝗲 tool. Inside the project directory, we have an 𝗖𝗂𝗲 folder where we can put the input files, in this case is a test video, and the configuration files for 𝗖𝗂𝗲. In the configuration file, we have different sections. The first one specifies the input files needed to trigger the application. The test can be either asynchronous or synchronous. If the test is being done synchronously, we can specify different intervals with varying throughput specified in requests per minute and different durations. In the component section, we can define for each component an array of parallelism level, which are the maximum number of instances that a component is allowed to have running at the same time. For each value in these arrays, a test is going to be performed. The tool can be launched from the AI Sprint Studio image with the AI Sprint profile command. When starting, the 𝗖𝗂𝗲 tool is going to list all the configurations that are going to be tested. It will deploy the infrastructure if they are not already up. This infrastructure will be cleaned from the remnants of past execution, so all services will be removed, the buckets will be removed or cleaned, and then it will configure it for the current test by deploying the correct services. It will then proceed to move the input file according to the specification of the configuration file to trigger the execution, and then it's just a matter of waiting for the execution to complete. Skipping to the end of the test, the tool is collecting the logs from Oscar and also from Kubernetes, and all the information inside these logs will be processed to generate a dataset with information on the runtime and the response time of the components and the application. And at the very end, it will generate the results in terms of datasets and graphs. To generate the machine learning performance model, it is sufficient to tweak out the configuration file for the ML library with the techniques that we want to use. We can now set in the 𝗖𝗂𝗲 configuration file the flag train models as true. And when relaunching the campaign, 𝗖𝗂𝗲 will notice that the data is already there, so it won't start from scratch. Instead, it will skip straight to generating the machine learning models. Now the library will automatically train different models, one for each technique. If hyperopt is enabled, it will also use that to fine-tune the parameters. And at the very end, it will test the generated models to figure out which one is the best, and it will return that.
In the following videos, we will present 𝗖𝗂𝗲𝗄𝗲, a design time tool to optimize the resource selection and placement of artificial intelligence application components. Once the application is profiled and performance models are available to predict the response times of all components on the candidate resources, it is time to select the optimal placement to start the application execution. What 𝗖𝗂𝗲𝗄𝗲 aims to provide is a tool that automatically explores different design alternatives, with the goal of minimizing the application execution costs while dealing with technology constraints, performance, and privacy requirements. In particular, 𝗖𝗂𝗲𝗄𝗲 will identify the optimal resources and the best component placement at each computational layer, which is crucial to orchestrate at best the heterogeneous computing continuum resources. Existing literature proposals address similar problems by proposing analytical models or heuristic solutions. For instance, the first work reported here aimed at optimizing the cost of serverless applications represented as directed acyclic graphs under performance constraints, or on the other hand, optimizing the performance under budget constraints. The second proposal develops a mathematical model to solve a task application problem among edge and cloud resources, minimizing the energy consumption while guaranteeing delay constraints. Finally, the third one tackles the service placement problem to minimize migrations, bandwidth consumption, and computational costs, determining the minimum number of CPUs that meet the latency requirements. Among these and other proposals, Space4AID is one of the first tools to consider resource contention in determining the optimal placement. Moreover, it focuses on artificial intelligence applications and considers multiple candidate neural network deployments, given by the possibility of partitioning components at different layers according to network and load conditions. This is the Space4AID tool architecture. It includes the Space4AID components and a parser that is used to convert the YAML files provided in the application directory into JSON files needed by the Space4AID tool. Space4AID receives as input the application directory, which includes a set of YAML files, describes the application graphs, which reports the set of components and the dependencies among them, including the transition probabilities between consecutive components, the candidate deployments and the candidate resources, specifying whether the components can be partitioned and where they can be executed. The input parameters for the Space4AID tool, including the list of heuristic methods that should be executed and the corresponding data. In particular, for each method, we specify the maximum runtime, both as an actual duration in seconds and as a maximum number of iterations. In particular, Space4AID implements a random greedy algorithm, which is always executed first to generate a pool of good quality candidate solutions, and a set of heuristic algorithms used to further reduce the costs. These include local search, tabu search, simulated annealing, and genetic algorithms, and are executed starting from the pool of solutions built by random greedy. Our design time problem is modeled representing applications as direct and acyclic graphs, whose nodes are the components. Edges represent the precedence relations and are labeled with the probability of transitioning from one component to the other and with the amount of transfer data used to compute the network delays. We consider as main performance metric the response time, which may be computed both for single components and for execution path including multiple components, imposing local and global computing continuum resources in functional service configurations. Each resource is characterized by a maximum memory capacity. Communications are performed through network domain characterized by different access delays and bandwidth. For instance, we can assume that edge devices communicate through the Wi-Fi while the cloud virtual machines in a cluster are connected through a wired network. Resources in the computing continuum are characterized by different costs. The costs of edge devices are estimated for a single run of the target application, amortizing the investment cost along the lifetime horizon of the device and dividing the yearly management cost by the number of times the application is run over 1 year. Cloud virtual machine costs are hourly costs, while functional service costs are expressed in gigabyte per second, and they depend on the memory size, the function duration, and the total number of invocations. Response times can be computed either by relying on the queuing theory or by developing machine learning-based performance models, as we discussed when presenting the 𝗖𝗂𝗏𝗏 framework. Summing them, the delays induced by data transmissions across network domains. Both queuing theory and machine learning models guarantee percentage errors between 10 and 30%, so they are reasonably accurate for practical purposes. In the following slides, I will report the results of some experiments testing Space4AID. We will compare the performance of the different heuristic methods as well as comparing Space4AID with a state-of-the-art method. To do this, we designed 3 scenarios at different scales, including between 7 and 15 components and a variable number of candidate resources and performance constraints. These will be light or strict constraints to test the Space4AID capabilities of determining good quality solution in an easier or a more complex setting. We compare the cost of different methods by defining the average percentage cost ratio as reported in the formula. These are the results achieved comparing the 5 heuristic methods in the different scenarios. To determine a solution, we always run random greedy first for a maximum fixed time, and then improve the solutions pool by one of the heuristic running for the same amount of time. We can observe that local search, tabu search, and simulated annealing obtain similar or better results than random greedy and genetic algorithms. In particular, local search is on average the best performing method. We then compare local search with a method called best cost under performance constraints, or BCPC, proposed in the literature. We can observe from the three scenarios that local search achieves an average cost ratio of 27% when it runs for the same time as BCPC, while it reaches 36% when it runs for 1 hour. Now, I will leave the floor to my colleague 𝗖𝗃𝗂𝗲 who will demonstrate how to run the Space4AID tool.
Now I run a Space4AID under 𝗖𝗂𝗂𝗄𝗲 Studio. As I already mentioned, after some profiling, we have some performance models for the prediction generated by TOSCARIZER. In a Space4AID folder, we can see a Space4AID YAML file that I already explained. Now I want to run the tool. In order to run the tool, we should mount the application directory into the Docker and run the Space4AID under 𝗖𝗂𝗂𝗄𝗲 Studio. As the input for Space4AID, we have to specify the application directory, that is a mask detection here, and then start running. The Space4AID first call a Space4AI parser to convert all the YAML file to the JSON file, because the tool was based on the JSON file. And then the tool run randomDB to find some feasible solutions. These feasible solutions are fed to the heuristic, which is taboo search here, to improve the result if it's possible. And at the end, a Space4AI parser convert the output JSON file to production YAML. Here we see the output JSON, and the production YAML file goes to 𝗖𝗂𝗂𝗄𝗲 deployments and optimal deployments. The production YAML shows the result. This file includes two sections. The first section is components that shows the optimal placement of each component. For instance, here the component 1 should be placed on VM2 and the component 2 should be placed on VM4. The second section shows the selected resources. For instance, here in computational layer 1, VM2 is selected, which is M4 large in AWS, and the selected resource in computational layer 2 is again VM4, which is M4 large AWS. At the end, it shows that the solution is feasible and the deployment name is base. It's because we don't have a partitioned components. The optimal configuration found by Space4AID, it can then be deployed through Infrastructure Manager, which is a 𝗖𝗂𝗂𝗄𝗲 orchestrator, by running the following command. First, we need to generate the Tosca templates for the recent optimal solution with the description of full virtual infrastructure needed to deploy all application components. For the correct Tosca configuration, a set of valid DNS names are assigned to the nodes to enable correct and secure external access to the services. So a Route 53 managed domain is required to make it work. We can set it with the domain parameter and we run it. So the Tosca file for plurifaces and the mask detector is generated in IAM folder under optimal deployment folder.
In the following videos, we will present Space4AI-R, a tool for the runtime management of artificial intelligence applications in the computing continuum. Determining the optimal application component placement at design time is not enough. What happens while the application is running? Variations in the environment conditions, for instance in the incoming workload, determine the need of monitoring the component's performance and possibly reconfiguring the running deployment. 𝗖𝗂𝗄𝗲 aims at automatically determine and perform these reconfigurations when needed, minimizing the execution costs while following workload fluctuations, coping with technology constraints, performance, and privacy requirements. Indeed, these workload fluctuations lead to resources saturation or underutilization, meaning that the current production deployment may become unfeasible or too expensive for the new environment conditions. Other literature proposals discuss how to react to dynamic environment conditions as the workload fluctuations. However, they mostly consider either scaling or offloading actions, instead of trying to determine a new solution both in terms of resource usage and components placement. As with 𝗖𝗂𝗄𝗲, the 𝗖𝗂𝗄𝗲 optimizer is one of the first tools to consider resource contention in determining the optimal placement. Moreover, it focuses on AI applications and considers multiple candidate neural network deployments, given by the possibility of partitioning components at different layers according to network and load conditions. As we have already discussed, the resource selection and component placement problem is initially solved at design time. We consider the maximum expected workload and identify the optimal solution that guarantees low execution costs and to meet the quality of service constraints imposed by users. However, this is not sufficient in practice. The input workload of applications usually fluctuates throughout the execution, so that the initial placement may become unfeasible if the workload increases, or incur in resources underutilization and overspending if it decreases. Therefore, the design time choices need to be updated at runtime, performing actions as resource scaling or component migration. We assume that this adaptation is performed periodically, and we design and propose a random search and stochastic local search algorithm to determine the new solution at each call. Note that most of AI application components are themselves deep neural networks, which can be partitioned as specific layers to offload part of the computation to different devices. At design time, a specific deployment may be selected. For instance, in this case, we cut the network almost at the beginning, offloading most of the computation to a second resource, maybe in the cloud. The choice can be reconsidered at runtime if the scenario varies. For instance, if the network connectivity becomes slower, it may be more convenient to execute most of the computation locally. This is the architecture of the AI Sprint runtime, which has its core in 𝗖𝗂𝗄𝗲. The runtime manager interrogates the monitoring system to retrieve information about the current application throughput and the component's response times. Based on the collected data, it asks the 𝗖𝗂𝗄𝗲 optimizer if and how the system should be reconfigured, and which is the new optimal components deployment. The changes are applied through TOSCARIZER and possibly the infrastructure manager. Similarly to 𝗖𝗂𝗄𝗲, the 𝗖𝗂𝗄𝗲 optimizer leverages random search and stochastic local search to determine the new solution, identifying a pool of good quality candidates and then enhancing the results by exploring the corresponding neighborhoods. In the following slides, I will present the results of the 𝗖𝗂𝗄𝗲 validation in 3 different cases. First of all, we ran a use case analysis considering the maintenance and inspection use case mentioned at the beginning, including 7 components and candidate resources from 4 different computational layers. We designed 3 scenarios considering 3 different maximum workload values and therefore 3 different resources selected at design time at the second edge layer. The workload profiles in the 3 scenarios are reported in the figure. From the plots, we can observe that the 4 global constraints imposed on different components paths are always satisfied in the 4 scenarios. The response times values are closer to the threshold in the second and third case, since the workload is generally higher and therefore it's more difficult to identify a feasible solution. We compare the costs achieved by 𝗖𝗂𝗄𝗲 with the cost of a static placement where the design time solution is kept fixed throughout the application execution. As we can see from the plot, the cost saving induced by the dynamic reconfiguration is always non-negative, meaning that 𝗖𝗂𝗄𝗲 always manages to find a solution at least as good as the design time one. The maximum saving, up to 60% for the third scenario, is achieved when the workload is minimum, since the design time solution is computed for the maximum expected workload, and therefore, when the workload is minimum, there's more space to optimize. We can also note that the average time required by SpaceFray R optimizer to determine a new solution is of the order of 0.4 seconds. To strengthen the observation that the time to solution is small enough to run the SpaceFray R optimizer in practical settings, we ran a scalability analysis including 3 scenarios and a number of components varying between 5 and 15. We randomly generate the application tags, including branches to consider a more complex settings, the service demands, and the response times constraints thresholds. These are the results we achieved. Again, we can note that the dynamic reconfiguration guarantees lower costs than the static placement, with a reduction up to 60% for larger systems. Moreover, the time to solution remains always between 0.4 and 1.5 seconds, which is almost 100 times faster than SpaceFray D. Finally, we compare the behavior of the SpaceFray R optimizer with a state-of-the-art method that is often exploited by public cloud providers to scale the cluster resources. This is based on setting a minimum and maximum utilization threshold and scale the number of resources if the current utilization exceeds one of them. We generate 4 scenarios with a variable number of components, setting a local constraint on each component response time. We also considered 3 different values of maximum workload and 3 different acceptable utilization intervals. As we can see from the plots, the SpaceFray R optimizer always achieves lower cost than the utilization heuristic, with a cost reduction between 10 and 40% on average. Moreover, it also manages to always satisfy the response time constraints, while the utilization heuristic incurs in a number of constraints violations between 1.8 and 35% when the load is higher. I now leave the floor to 𝗖𝗂𝗃𝗲𝗄𝗲 to demonstrate the use of SpaceFray R and the runtime manager.
Let's see the 𝗖Sprint runtime in action. We will have an application deployed on the cloud, and we will adapt the configuration of the application based on the changed network condition.